Last time we proved the existence of the Mayabotore sequence and used this to compute the homology groups of the spheres. As a corollary, of those computations, we obtain if n is strictly greater than 0, then Sn is not homotopy equivalent to a point. If Rm is homeomorphic to Rn, then M is equal to N. So to see this, note that if there is a homeomorphism from Rm to Rn, this implies that there is a homeomorphism from Rm minus a point to Rn minus a point, and Rm minus a point is homotopy equivalent to Sm minus 1, and Rn minus q is homotopy equivalent to Sn minus 1. Thus, we get M is equal to N by looking at the homology. Next, we define homology of pairs. And prove the theorem on accession. So let A contain X be a subspace. Then we have the inclusion of complexes and this gives a quotient complex which we denote. So thus we have a short exact sequence of complexes and a long exact sequence of homology groups. So the homology groups of C dot x comma a are denoted as H dot x comma a, and so on. Now suppose we have subspaces Z contained in A contained in X. So consider the map of complexes So it is easy to see that the kernel of this composite map of complexes is the complex C dot A minus Z. Thus, we have an inclusion of complexes so this is by our notation. This is inside. And the first theorem we are going to prove is be such that the closure of Z is contained in the interior of A. Then the inclusion induces an isomorphism on homology. So let us prove this. So let U be the collection of sets A and x minus Z. Then x minus Z contains x minus Z closure, and this is open, which implies interior of x minus Z contains interior of x minus Z closure, which is equal to x minus Z closure. And from this we get x is equal to x minus Z closure union interior of A, which is equal to so in this situation, we had seen that the subcomplex corresponding to this collection U induces an isomorphism on homology. Recall that C dot U is the image of the map of complexes Thus, from the long exact homology sequence, we get that as homology group 0. So it is also clear that the co-kernel of the map of complexes C dot x minus z to C dot x by C dot a is C dot x mod C dot u x. Thus, we have a short exact sequence of complexes So from the long exact homology sequence, it follows that Hn x minus z comma a minus z is isomorphic to Hn x comma a for all n. So this proves the theorem. As a corollary, we get that U in Rm and V in Rn be open sets such that U is homeomorphic to V. Then M is equal to N. So if there is a homomorphism from U to V, then it follows that U minus P, so HI U comma U minus P is isomorphic to HI V comma V minus P for all I. So we will show that from HI U comma U minus P, we can recover the integer M. So let's see how to do this. So let D be a small closed disk around P, and let Z be equal to U minus D. Then Z bar is contained in U minus P. And by the excitation theorem, we have HI U comma U minus P is isomorphic to HI U minus Z comma U minus P minus Z. This is isomorphic to HI T comma T minus P. So let us compute HI T comma T minus P. Case 1 is when M equal to 1. So in this case, we have D minus, let's say P is 0. This is the disjoint union of two copies of R with homomorphic to the disjoint union of two copies of R. So from the long exact sequence, for pairs, we get HI of D thus, if I is strictly greater than 1, then HI of D comma D minus 0, 0. If I equal to 1, then we have so since the map H naught D minus 0 to H naught D, so H naught D minus 0 has two connected components, so this is isomorphic to Z2, and this map, this is isomorphic to Z, H naught D, and this map is surjective. In fact, this map is just A comma B goes to A plus B, where we have identified 1 comma 0 and 0 comma 1 with classes of points in each component. So since it is surjective, it easily follows that h1 t comma d minus 0 is isomorphic to z, and h0 t comma d minus 0 is 0. So case 2, when m is strictly greater than 1. So in this case, we have so thus when I is strictly greater than 1, we get that hi of t comma d minus p is equal to hi minus 1 of t minus, this 0. But this t minus 0 is homotopy equivalent to the sphere Sm minus 1, and so this is z if I minus 1 is equal to m minus 1, so that's if I is equal to m and 0 otherwise. Since I is greater than 1, when I is equal to 1, we have so this time, since d minus 0 is connected, is path connected, it follows that h0 t minus 0 to h0 t is an isomorphism, which implies that both h1 t comma d minus 0 and h0 t comma d minus 0 are 0. Thus, in all cases, we conclude that we may recover m as the unique integer for which hi u comma u minus p, which is isomorphic to hi d comma d minus p, is non-zero. Thus, m is equal to m. So this proves the overall. So let f from x to y be a continuous map. We write f is a map of pairs from x comma a to y comma b if f of a is contained inside b. And the next theorem we want to prove is that f and g from x comma a to y comma b be maps of pairs. Assume that they are homotopic through a homotopy of pairs that is, there is a homotopy f such that each ft is a map of pairs from x comma a to y comma b. Then the induced maps on homology are the same. So proof. So it is clear that f and g induce maps of complexes f dot and g dot from c dot x comma a to c dot y comma b. So it suffices to show that both these maps of complexes are homotopic. So since f and g are homotopic, using the homotopy we had constructed, the prism operators Pn from Cnx to Cn plus 1y. So it is easily checked from the definition of Pn that Pn of Cna is contained in Cn plus 1b. Thus, the Pn's induce maps Pn bar from Cn x comma a to Cn plus 1 y comma b. And these will give a homotopy between f dot and g dot. So this is checked easily. So this completes the proof of the theorem. So next we prove the following proposition. Let A contain V contain X and assume that A is a deformation retract of V. Then the map induces an isomorphism on homology. So proof. So consider the following short exact sequence of homology groups of complexes. It's the following diagram. So from the homology sequences, we get the following commutative diagram. So because V deformation retracts onto A, these maps are isomorphisms. And now the proposition follows using 5 lemma. So let A containing X be a closed subspace. We shall denote by X mod A the space obtained by collapsing A to a single point. And the topology is the quotient topology. So we shall denote this point by A mod A. So thus we have a map of pairs Q from X comma A to X mod A comma A mod A. So the theorem close subspace, and assume that there is an open set V such that V deformation retracts onto A. Then the map Q lower star from Hn x comma A to Hn x mod A comma A mod A is an isomorphism. Proof. So consider the following commutative diagram. So the arrows 1 and 3 are isomorphisms due to the previous proposition. The arrows 4 and 6 are isomorphisms due to accession. Arrow 5 is an equality since x minus A is equal to x mod A minus A mod A, and V minus A is equal to V mod A minus A mod A. Thus, it follows that Q lower star is an isomorphism. As a corollary, we get the following with notation as above. we get that for n greater than equal to 1, hn x comma a is isomorphic to hn x mod a. This is because when n is greater than equal to 1, the natural map hn x mod a to hn x mod a comma a mod a is an isomorphism. This is an easy check. And this left as an exercise. So we will end here.